doing that. Especially traders are interested in doing that. Traders are interested in finding out whether 3-month options are relatively more or less undervalued compared to 6-month options, for instance. But they really cannot do that right away with all the inputs that go in. So they'd like to focus on, to zero in on one number. And the number that they usually focus on is the implied volatility. So they can use the Black-Scholes model in reverse, and they can put all these inputs, S, X, R, the time to maturity, and the price, the call option price, or the put option price, and get an implied volatility number. All right? And then they can compare whether one option is relatively more undervalued compared to another. For instance, if the implied volatility on 3-month Deutsche Mark options is 10%, while the implied volatility on 6-month Deutsche Mark options is 11%, which options are relatively more overvalued? 3-month options, implied volatility 10%, 6-month options, annualized implied volatility 11%. Which option is comparatively more overvalued? Anybody? The
one with the higher volatility.
Right. The one with the higher volatility is relatively more overvalued. Volatility, as volatility goes up, so does the option price. And therefore, this would indicate that 6-month options are relatively more overvalued than 3-month options. Okay. Are there any questions about looking at the Black-Scholes model as if it were a black box, and what are the inputs that go into the black box, into this black box? What are the outputs, and how this black box can be turned around and used in a different way?
Can you maybe explain why we use the risk-free rate also as an input?
Okay, very good question. As opposed to the appropriate, let's say, the euro-dollar rate or the funding cost of the Chase Manhattan Bank. Okay. Again, it takes me a little bit out of the usual course of events, but let me say that a call option is equivalent to buying a certain amount of shares and borrowing money. Okay? That is to say, and this was the ingenious insight of Black and Scholes. Many people had thought about how to derive an option pricing formula, and they were unable to find a closed-form solution for it, even using very, very high mathematics. But the insight, the ingenious insight of Black-Scholes was that they said that a call option equals being long in stock and borrowing money. And it's really very important that you feel comfortable with that. At section 4 of the presentation, I can even derive this mathematically and tell you more precisely what the proportions are. But intuitively, please try and feel very, very comfortable with that. That a call option is equivalent to buying a certain amount of shares in the stock and then borrowing money. Now, let me try to motivate this intuitively. Now, what's a call option? You buy an option for a small amount of investment, and if the stock finishes in the money, if it does well, then you've had a huge return on your investment, right? And if the stock finishes out of the money, you've lost everything that you've invested, right? So intuitively, what is a call option? Intuitively, the return on a call option is really good when times are really good, right? And the return on a call option is really bad when times are really bad, right? You lose everything that you've invested in. All right. What is that like? Bankers should know that off the bat. If times are really good, if you do really well when times are good, and if you do really poorly when times are bad, what is that like? What kind of a company is that? That's a highly leveraged company, right? That's a highly leveraged company. If you have a highly leveraged portfolio or a highly leveraged company, you do really well when times are good, and you do really poorly when times are bad. And what is this? Being long in stock by borrowing money. If you've bought stock by borrowing somebody else's money, you will do really well if your stock goes really high up. You just pay back what you've borrowed, and you'll do really poorly if the stock does not do that well, right? Because you'll have to pay back what you've borrowed, correct? That is a leveraged portfolio. This is the only intuitively plausible way that I can motivate this insight that Black-Scholes had, that a call option is equivalent to being long in stock and borrowing money. Okay. I have not forgotten your question, because your question is, why is the risk-free rate of interest relevant? And here I've gone into explaining this. Now, so that says that you have two portfolios, a call option on the one hand, and then the other portfolio that consists a little bit of the underlying stock and the money that you've borrowed. And this says that these are identical portfolios, that no matter what will happen to the world, their returns will be identical. Therefore, you can arbitrage between these two portfolios. And therefore, arbitraging between these two portfolios is risk-free. And therefore, by forming an arbitrage mechanism via which you can sell call options, and then you cover yourself by buying delta shares of the stock, that's where delta comes in, and borrowing money, you really only expect to make the risk-free rate of interest rate. And that is why the risk-free rate of interest is there, and not Chase Manhattan Bank's marginal funding rate or some other interest rate. It's based on this notion that we are replicating portfolios and arbitraging between these portfolios in a riskless free rate, and therefore in a riskless way, and therefore it is the risk-free rate of interest that matters other than anything else. Let me talk about the deterministic world. What would the price of a call option look like if we're living in a deterministic world? Okay. Now, what is the price of a call option, the intrinsic value of a call option at maturity? What is the intrinsic value of a call option at maturity? A call option at maturity, by a star, I will mean the maturity value. Sorry?
The value of the stock minus the strike price.
The value of the stock minus the strike price, right? That is the value of the call option at maturity, the intrinsic value. Okay. We are living in a deterministic world. Okay. Before maturity, what will be the value of this call option? It will be the discounted present value of this, right? It will be the discounted present value of the stock at maturity, correct? Okay. So this will be S star over 1 plus R, where here I use R as the risk-free rate of interest, as opposed to the handout where R stands for 1 plus the risk-free rate of interest. But you might as well get used to this changing notations from paper to paper and presentation to presentation. It just comes with the territory. Okay. All right? So is everybody with me? In a deterministic world, the value of the call option today would be the present value of the stock at maturity, discounted, right? But we have to be careful. I assumed here it's only 1 year, so I have to say 1 plus R to the T, right? Where R is the annualized interest rate, and T is the time to maturity in years, right? And similarly, I have to say 1 plus R to the T here. Again, I would ask you to really grasp this formulation. This is the only way I can think of demystifying the Black-Scholes model. First, we look at the deterministic model. Is everybody comfortable with that? The current price of the call is the maturity value of the stock discounted to the present, right? Minus the strike price that you have to pay at maturity discounted to the present. Are there any questions about that? Okay. Now, the Black-Scholes model assumes that the stock grows at the risk-free rate of interest. Okay? Now, if the stock grows at the risk-free rate of interest, what is S star equal to? S star is equal to S into 1 plus R to the T. Okay, it grows at the risk-free rate of interest. Okay, so then we have here S minus K into 1 plus R to the minus T. Okay, this is the price of a call option in a deterministic world. We have S, the stock price here. We have the stock price minus the discounted present value of the exercise price, right? Does anybody have questions about that? Again, remember, the R here is just the risk-free rate of interest. In the handout, the R is defined as 1 plus the risk-free rate of interest. Now, let's talk about the put. Again, in a deterministic world, how should the price of a put option look like? And I urge you to work it through yourselves. That's, I think, the best way to feel comfortable with this formula. Okay, so in a deterministic world, at time to maturity, what will the put price look like? What will be the intrinsic value of the put option?
K minus C.
Sorry?
K minus S star.
K minus S star. Right? And is everybody comfortable with that? At time to maturity, the intrinsic value of the put option will be the exercise price minus the stock price of the stock price at maturity. It cannot be negative, of course. It's either 0, or if the stock price is less than the exercise price, it will be positive, right? Okay. And how do we bring that to the present time? How do we bring that to the present time? Sorry?
Discounted.
Okay. Okay, so we discount K. So we say K into 1 plus R to the minus T. And how about this?
S star times parentheses 1 plus R minus T star is S times 1 plus R to the T.
And therefore, the 1 plus R to the T and the 1 plus R to the minus T cancel. We just have S here. Okay. We first looked at the put value at maturity in a deterministic world, and we discounted that to the present, and this is the put value at time before maturity in a deterministic world. In a stochastic world, and I cannot go into the derivation right now, but again, maybe in the last part of the presentation, we'll go into these extensions. In a deterministic world, the formula look very similar to the, in a stochastic world, the formulae looked very similar like a deterministic world, except that there are some correction factors, if you will, that change the world from being deterministic to stochastic. If you look at page 4 of the handout, you have the price of a call option when the world is deterministic. Okay. What was our deterministic formula? What was our deterministic formula? S minus?
K times 1 plus R to the minus D.
Okay. Now, when the world is stochastic, we will have an adjustment factor here and an adjustment factor there. Okay, so the adjustment factor is, what is the adjustment factor that comes after S? That's n of x, where n is the normal density function,